Good morning,
Good
sir.
morning, sir.
Good morning. So, without wasting any time, let us start with the discussion. So, if you remember, last class we have been discussing about the complexes and splitting in complexes. We have understood how the splitting happens without looking at animation parts and all. Yes or no? In the octahedral complexes, yeah, in the octahedral complexes, the splitting of 5d orbitals occurs into two sets, which are called as T2G set and EG sets. T2D set will contain dxy, dyz, dzx. EG set will contain dx square minus y square dz square. And what was the reason for the splitting? The main reason for the splitting is all the d orbitals do not experience same repulsions from the ligand. All the d orbitals do not experience same repulsions from the ligands. Those d orbitals which experience more repulsion, they will be increasing energy. Those d orbitals which will be experiencing less repulsions, they will be decreasing in energy. In the same way, tetrahedral complex splitting also seen. So if you look at tetrahedral splitting, whatever the ligands which we have, which has lobes in between the axes, they will experience more repulsion. That is why T2 is up and E is down. And in the square planar complex also we have seen dx square minus y square will experience highest splitting, then dxy, then dz square, and then you are going to have dxy, dxz and dyz. So let us look at the same in the animation point of view. What was the first point, students? The first point is, according to CFT, central metal ion is considered as a positive point charge, anionic ligands as a negative point charge, neutral ligands as a point dipole. Central metal ion is considered as positive point charge, anionic ligand as negative point charge, neutral ligand as a point dipole, and attraction between metal ion and ligand. Metal ion and ligand, whatever the attraction they have, that will be electrostatic in nature. After this, we are studying in the electric field of ligands, the 5d orbitals of the metal atom no longer have exactly same energy, while they are split into two different energy levels. So T2G stands for dxy, dyz, dzx, which are also called as non-axial d orbitals. That means their lobes are not present along the axis, e.g. dx square minus y square dz square, these are called as axial d orbitals. We can say their lobes are present, axial means the electron density, the lobes are present along the axis. Right? So these are the shapes of d orbitals. We all know dxy, dyz, dzx. If you look at their shapes, dxy, that will be in the xy plane and in between the axis. Dxy means the double dumbbell will be present in the xy shape, xy plane, and you will be having the lobes in between the axis, not along the axis. dyz, look at dyz. Obviously, it should be in the yz plane. Of course, yz plane. So in the along the x-axis, you will not have any electron density. And obviously, if you look in the yz plane also, the lobes are present in between the axis. Same with the dxz. In the xz plane, we have the electron density. In the xz plane, we have the electron density, and lobes are present in between the axis, not along the axis. Dx square minus y square. So we have lobes along the axis of x direction and y direction. And dz square, you will be having electron density along the z axis, and you will have some electron density in the xy plane also. These are the shapes of 5d orbitals. Is this clear, students? D orbital shapes you might be knowing.
Yes, sir.
Yes.
Yes, sir.
Yes, very good. So indirectly you can see, since these orbitals are obtained from quantum mechanical model of an atom, so whatever the complexes you are explaining, everything is based on the quantum mechanical model of an atom. Okay. So Bohr's theory cannot explain all these things very correctly. Everywhere you are talking about orbitals, everywhere you are talking about overlapping. So that means you are indirectly relating the quantum mechanical model of an atom, which is obtained from your Schrodinger's equation. So in octahedral complex, the coordination number is 6, obviously. Coordination number will be 6 because 6 ligands are there, or 6 coordinate bonds are formed if we have more than one type of ligand. Like if you have bidentate ligand, tridentate ligand, then you don't have 6 ligands. Instead, you will be having 6 coordinate bonds. The metal ion is at the center, and the ligands occupy the 6 corners of the octahedron. Metal ion is exactly the center, and ligands occupy 6 corners of the octahedron, as shown in the figure. So does this look like octahedron or not? You try to connect all these ligands, but there is no connection in reality. Here, if you look at the figure, the ligands, one ligand and the other ligand, they were connected by blue dots, blue colored dot lines. So that doesn't mean like ligands are in reality connected. We are just understanding how the picture is, how the diagram looks like. So when you try to connect all the ligands, you are going to generate a figure which is called as octahedron. Yes, that is how your octahedron looks like. This is the main point. The two orbitals dx square minus y square dz square and are assigned as EG orbitals, which are the while the 3 dxy, dyz, dzx are designated as T2G orbitals. As the 6 ligands approach the central metal ion along the axis, EG orbitals is repelled more by the ligands than the T2G orbitals. Is that point clear or not? As the 6 ligands approach the central metal ion, EG orbitals repel more when compared to the T2G orbitals. Same point, because EG orbitals have lobes along the axis, ligands are also coming along the axis, the repulsion experienced by EG orbitals is greater. So repulsion is greater means energy would be greater, obviously. So in other words, the energy of the EG orbitals increases much more than that of the energy of the T2G orbitals. So ligand are donating their lone pairs, d electrons of the metal, they start repel. Write down all of you this figure. So this is the energy. In the absence of ligand field, d orbitals of the metal are degenerate, and we have 5 d orbitals like this. In the presence of ligand field, energy of d orbitals is increased, and all the 5 d orbitals again still have same energy. So what type of field is this? Initially, in the absence of ligand field, 5 d orbitals have same energy. Then what they are saying, in the presence of ligand field, energy of d orbitals is increased. And if you look at all the d orbitals, they have same energy or not? So what type of field is this? What type of field is this? Is it a field of, is this the scenario in the octahedral complex or tetrahedral complex or square planar complex? This is happening in which type of complexes? Anyone?
sp3d2.
Yes, Faizan? sp3d2. See, if you look at this scenario, every d orbital energy has been increased and all the 5 d orbitals have same energy. So what type of complex is it, students? It is not a complex, it is like a spherical field. Yes or no? In a tetrahedral complex, in a square planar complex, or in a octahedral complex, the 5 d orbitals will not have same energy. Here we do have same energy, but all the 5 d orbitals energy has been increased. So ligands are approaching from all the directions like a spherical field. Now the splitting will occur, and this center or this point where the energy of all the 5 d orbitals is same, that is said to be Barry center. and this is your T2G orbitals. These are your EG orbitals, and delta naught O or delta O, that represents the crystal field energy of octahedral, or you can say the energy difference between the T2G and EG levels in the octahedral complex. All of you note down this diagram. From this, we can also calculate crystal field stabilization energy, CFSEs. And this is the splitting of T2G and EG. This happens in the octahedral field. Octahedral field. This is in the absence of ligand. This is in the presence of spherical field. And this T2G and EG, that is in the presence of octahedral field. And can I compare the energy of T2G and this absence of ligand? Out of these two, which is greater? Out of these two, which should be high? Which should be higher in energy?
T2G.
T2G has to be higher in energy, right? Because T2G experience some repulsions. Although less repulsions when compared to EG, but they have some repulsions because ligands are approaching. So when compared to your no field or absence of ligand field, the T2G should be high in energy. So T2G is somewhere high. Okay, write down that point also. T2G should be high in energy when compared to degenerate d orbitals in the absence of ligands. T2G should be high in energy when compared to degenerate d orbitals in the absence of ligands. This is nothing but your barycenter. And how can you calculate crystal field splitting energy or crystal field stabilization energy? Like for example, let us say, yes, Ayushi. How to calculate CFSE, students?
By counting the number of electrons T2G and EG.
Yeah, let us say number of electrons in T2G is X, number of electrons in EG is Y. So CFSE should be equal to, you can write this formula like this. We have X electrons in the T2G. So X, the energy of the T2G, like T2G means how many d orbitals are there? 1, 2, 3, 3 d orbitals are there. EG means 1, 2, 2 d orbitals are there. Whatever the decrease in the T2G energy, that should be compensating the increase in the energy of EG or not? What will be the decrease in the T2G energy? That should be compensating the increase in energy by EG. So how much is increased in the EG? So out of 5 orbitals, 2 orbitals have been raised. So 2 by 5. Understood this point carefully. Why I have written 2 by 5? We have 5 d orbitals. They split into 2 levels like T2G level and EG level. The T2G level is decreased in energy. How much is decreased? We don't know. But what I can say, the decrease in energy of the 3 d orbitals should be compensated by the increase in energy of 2 d orbitals of the EG. So 2 by 5 times out of delta naught or not, but with a plus symbol or minus symbol. Since energy is decreased for the T2G, minus symbol. X is the number of electrons in the T2G into minus 2 by 5 delta naught plus Y is the number of electrons in the EG. How much energy is increased for Y? For the EG set, I don't know. What I know? The amount of energy increased for the EG level, that should be compensated by the 3 d orbitals which were decreased in energy. So 3 by 5 and EG level has been increased. So plus sign 3 by 5 delta naught. So X into minus 2 by 5 delta naught plus Y into 3 by 5 delta naught. That is nothing but your minus 0.4 X plus 0.6 Y into delta naught. This is just because of splitting, and we can also have some pairing and plus NP. NP stands for number of electron pairs. N stands for number of electron pairs. Write down this formula. CFS is equals to minus 0.4 times that of X. X stands for number of electrons in T2G. Y stands for number of electrons in EG. Minus 0.4 into X plus 0.6 into Y times delta naught. What is delta naught? The total energy difference between T2G level and EG level, plus NP. N stands for number of electron pairs in the process of filling electrons. So while you are filling electrons, you will be having some pairs, no, electron pairs. So that NP. All of you note it down, students. Note it down and let me know. Done, Vaidehi, very good. What about others?
Done, sir. Done, sir.
Done. Done, very good. Okay, the electronic configuration in the n-1 d orbital depends upon following two energies. In the n-1 d orbitals, whether the electrons are going to be filled or not, that will depend upon following two energies. Delta naught, crystal field splitting energy, how much the splitting happened, and second one is pairing energy. If we have a strong field ligand, the splitting is very high. If the splitting is very high, the electron go and pair. They cannot go to the higher energy EG. If the splitting is less, the electron can go to the EG. That's the only point. Okay. In the presence of strong field ligand, the splitting energy is greater when compared to pairing energy. So what will happen here? So here pairing of electrons occurs. Pairing of electrons occurs. In the presence of weak field ligand, the pairing energy is greater when compared to your splitting energy. So here electron goes to higher energy level or higher energy EG level. Without pairing, the electron will be going into the higher energy EG level in the case of weak field ligand, and in the presence of strong field ligand, the electron pair up in the T2G level itself, so that you will be getting the more number of paired electrons. So let us look at the electronic configuration of D1, D2, D3, D4, so on up to D10. So in the presence of strong field ligand, how it happens? So we have splitting happened. Like energy difference, you can say energy difference is very high. Yes or no? In the presence of weak field ligand, splitting happened, the energy difference is less. Delta naught is less. Simple logic, students. We strong field ligands means the difference between the T2G level and EG level is high. Weak field ligand means the difference between the T2G level and EG level is less. Yeah, try to write the D4 configuration. Strong field ligand and weak field ligand. Strong field ligand, weak field ligand. In the strong field ligand, what happened to D4? The first electron goes into T2G, obviously no choice. Second electron also goes into T2G in the different d orbital without pairing. Third electron same again in the T2G without pairing. Fourth electron pairs up. Yes or no? Fourth electron is going to be pairing up in the presence of strong field ligand. Why? Because this delta naught is higher. In the weak field ligand, what is going to happen? First electron, second electron, third electron goes into T2G. Fourth electron goes into EG. Fourth electron will be going into EG. So if you write the electronic configuration, D4 strong field ligand means T2G3, T2G4. Yes or no? T2G4, EG0. D4 weak field ligand means T2G3, EG1. So because of this different filling of electrons, what do we have in the presence of strong field ligand? The D4 configuration will be having 2 unpaired electrons, whereas in the presence of weak field ligand, the D4 configuration will have 4 unpaired electrons. So obviously there will be a change or there will be a difference in the magnetic moments or not? Yes or no? Number of unpaired electron changes, so magnetic moment changes. And obviously, is there a difference in the type of complexes which are formed? Like in the strong field ligand, we have the EG level empty. Since EG level is empty, so the inner d orbitals can be used. These are n-1 d orbitals. These n-1 d orbitals can be used in the hybridization. Whereas in the weak field ligand, they are also fields, so they cannot be used. So like that, you will be understanding all the points in the case of strong field ligand as well as in the weak field ligand. Is this clear to everyone?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Yes, very good. So obviously low spin complex and high spin complex, why? Low spin because pairing happened, so spin decreased. High spin, pairing did not occur, so spin has been increased. D5 configuration, write down D5. In the same way, what is the electronic configuration of a D5 system in the presence of strong field ligand? SFL, strong field ligand.
T2G5 EG0.
T2G5 EG0, very good. In the weak field ligand,
T2G3 EG2.
T2G3 EG2, very good. So that will be scenario. Can I say for D1, D2, D3, irrespective of ligand, the configuration is same? Yes or no? For a D1, D2, D3, whether you have a strong field ligand or weak field ligand, the first electron, second electron, third electron, they will be entering into the T2G level only. They will not go into the EG level.
Yes.
Similarly, for D8, D9, D10 also we have the same scenario or not? So let us write for D5 you have written, right? D6, comment on D6. D6 strong field ligand. Weak field ligand. T2G6 EG0. Weak field ligand T2G3 T2G3 or T2G4?
T2G4.
EG2, right? D7. T2G6 EG1, so strong field ligand.
EG1.
Weak field ligand T2G5 EG2. EG3 or EG2? EG2, no? D8 strong field ligand, weak field ligand. D8, like you are adding one more electron. Strong field ligand, one more electron to D7. Strong field ligand, you have T2G6 EG0. What do you have now? So here EG1, right?
Yes, sir.
Yes. D7. Just a second, students. Sorry, students. Okay, fine. D8 means in the presence of strong field ligand, you will be having T2G6 EG2. In the weak field ligand also we have T2G6 EG2 or not?
Yes, sir.
So D8 and D9 and D10 will also have same configurations. So strong field ligand. So electronic configuration same means same properties. Nothing is going to change. So D9 will be T2G6 EG3 D9 weak field ligand, T2G6, EG3. D10. Yes or no? D10 would be again strong field ligand, or weak field ligand. We have T2G6, EG4, T2G6, EG4. So I can say D1, D2, D3, same configuration. D8, D9, D10, same configuration. And can I say D1, D2, D3, D1, D2, D3 complexes will have what type of hybridization? Octahedral complex. I am talking about T2G means octahedral complex only. Okay. D1, D2, D3. If the electronic configuration is D1, D2, D3 for any type of complex, so what will be your hybridization?
Octahedral.
Hybridization. Octahedral is the complex geometry. Hybridization.
sp3d2.
Sure. Look carefully. D1, D2, D3. The electrons, where are they filling? They are filling in the T2G only.
d2sp3.
Yes or no? So they are filling in the T2G1, 0, T2G1, EG0, T2DG2, EG0, T2G3, EG0. For strong field ligand or weak field ligand, doesn't matter. D1, D2, D3 means D2, sp3. Very good. And all are paramagnetic or diamagnetic? D1, D2, D3?
Paramagnetic.
All are paramagnetic because we have an unpaired electron. D8, D9, D10. In the D8, D9, D10, do we have any available orbitals? Inner available orbitals?
No, sir.
No, right? So what should be the hybridization?
sp3d2.
sp3d2. And all are paramagnetic or all are diamagnetic? Or is there anyone diamagnetic? So D8, D9 paramagnetic except D10. Except D10, all are para. Because D10 means T2G6, EG4, right? So that is going to be diamagnetic. Now you have a question. D1, D2, D3 configurations, D2, sp3 paramagnetic. D8, D9, D10 configurations, sp3, D2, and except D10, all are paramagnetic. Now the question stands for D4, D5, D6, and D7. D4, D5, D6, D7. Which is going to happen in the presence of strong field ligand? What is the scenario? D4, D5, D6, D7, strong field ligand. What will happen now, students? What is the hybridization? Geometry is octahedral because all these are octahedral complexes. D4, D5, D6, D7 configurations I am taking. In the previous case also we have taken the D4. No, here D4 configuration we have seen T2G 4 EG0. That means in the D4, in the presence of strong field ligand, do we have EG sets available for the hybridization or not? Yes or no?
Yes, sir.
So in the T2G, in the same way, in the D5 also, in the same way, in the D5 configuration also, in the strong field ligand, we have EG available. EG0 means no electrons in EG. That means EG set is vacant. In the D6 also, you see T2G6 EG0. So D4, D5, D6. Okay, sir. You are saying there are no electrons in the EG. So we can say D4, D5, D6 strong field ligand means what will happen? So we agree with you with the D4, D5, D6 strong field ligand. So in this case, D2, sp3, that would be the hybridization. Okay, that's fine. And same D4, D5, D6 weak field ligand. So what happens in this case? D4, D5, D6 weak field ligand.
sp3d2.
sp3d2. Now what will happen in the case of D7? D7 strong field ligand. Sir, you may argue like sir T2G6 EG1. So EG is not a vacant now. T2G6 EG1. So what will happen in the case of D7 a strong field ligand? D2 sp3 or sp3d2? Yesterday we have discussed one point. So that's why all those are important. I have told about transference of electron. How many of you remembered? Transference of electron. Yes or no? In the
Electron
D7.
will go to positive.
Yeah, in the D7 configuration strong field ligand case, T2G6 Eg1, T2G6 Eg1. Although you have one electron in the Eg level, that one electron will be going into the 4D. Yes or no? And you will be having vacancy here. So you will be having D2sp3 due to transference of electrons. And the D7 weak field ligand sp3 d2. Yes or no? Weak field ligand means sp3 d2. D7 strong field ligand means d2sp3 due to transference of electrons. Understood how the electronic configurations can be written? D1 to D10. So I'll repeat again. Listen carefully. D1, D2, D3. If the complex has D1 configuration or D2 configuration or D3 configuration for the metal ion, they are said to be having the hybridization of D2sp3. All are paramagnetic in nature, no doubt in that. In case in the complex, if the metal ion has D8, D9, D10, then all those complexes will have sp3 D2 hybridization, and all are paramagnetic except D10. So out of D1 to D10, 6 configurations are done. D1, D2, D3, D8, D9, D10. 4 are left out. What are those 4? D4, D5, D6, D7. D4, D5, D6. In the presence of strong field ligand, you have vacancy in the Eg. In the Eg, you do not have any electrons present. So obviously inner shells are vacant means D2sp3 is a hybridization. Based on the number of electrons, number of unpaired electrons, we can predict paramagnetic or diamagnetic. D4, D5, D6 weak field ligand means the inner electrons are not the inner orbitals are not available. So what happens in that case? sp3d2, that will be your hybridization. What is the hybridization? sp3d2. In the D7 strong field ligand, you still have one more electron in the Eg. That means you can argue like vacant orbital is not available. But still D7 strong field ligand, transference of electron occurred for the 4D. So because of that electron transfer, the Eg becomes vacant. So D2sp3 will be the hybridization for D7 strong field ligand. sp3d2 will be the hybridization for D7 weak field ligand. Is that clear, students? Yes or no?
Yes, sir.
Yes. Right. Similarly, D6 configuration, as I have told you, we can write down in the T2G and Eg levels. Electrons in the case of strong field ligand and weak field ligand. So if you want, you can note down this table. No need to note down. You can just understand how the things are happening. DN configuration, strong field ligand means pairing will occur. Weak field ligand means the electron goes into the Eg level. PE stands for pairing energy, delta naught stands for crystal field splitting energy in the octahedral complex. Yes or no? PE stands for your pairing energy, delta naught stands for crystal field splitting energy in the octahedral complex. The same configurations we have written. Can I proceed further? The same configurations I have written in the previous slide.
Yes.
D1 to D10.
Yes, sir. Yes, sir.
Very good. Yeah, this is a short trick for finding hybridization, magnetic moment and spin. Directive, what you can say? D1, D2, D3, D2sp3 paramagnetic, you don't need to see the ligand. Don't see the ligand if it is D1, D2, D3. D8, D9, D10, don't see the ligand. sp3, D2, all are paramagnetic except D10. D4, D5, D6, D7. Then you have to look at the ligand. Strong field ligand means D2sp3 and low spin. Weak field ligands means sp3, D2, high spin. and it depends upon the nature of ligand. Note down this short trick. Note down the same thing which we have discussed earlier, and just list it down once again. Note it down, all of you. And after noting this, try to solve this example. CrNH3 taken 6 3 plus. What is the magnetic moment? What is the electronic configuration of a metal ion? What is the hybridization? And what is the spin? What is the number of unpaired electrons? What is the spin only magnetic moment? All this you comment. Hybridization. What is the hybridization? First write down the electronic configuration of chromium. In this particular complex, chromium is in which oxidation states? 1 chromium is there. 1 into X, 6 ammonia, 6 into 0, that should be is equal to +3. So chromium should be in the +3 state. Electronic configuration of chromium, argon 4s1 3d5. Chromium in the +3 state, argon 4s0 3d3. So chromium +3 we is having D3 configuration. D3 configuration. Yeah, D3 configuration. Do we need to look at the ligand or any ligand? So no need to, yeah, no need to check ligand. No need to check ligand. So what will be the electronic configuration? T2G3 Eg0. Electronic configuration of D3 will be T2G3 Eg0 according to CFT. And what will be the hybridization? Eg0 means hybridization should be sp3 to, yeah, D2sp3. D2sp3 will be the hybridization. What about spin? Low spin or high spin?
Low.
Spin not defined. Okay. Although inner orbitals are used, because of the usage of inner orbitals, do we have any pairing?
No, sir.
Because of inner orbitals usage, if pairing of electron occur, then only we should say low spin. Spin has been decreased. Okay, spin not decreased, not increased. So spin is not defined. What type of complex is it? Inner orbital or outer orbital? Inner orbital complex. Because inner orbitals are used. How many unpaired electrons are there? Number of unpaired electrons?
3.
3. So what is the magnetic moment?
Paramagnetic. 3.
Yeah, 3 point something we can write directly write. Number of unpaired electron 3 means you can write 3.83 Bohr Manhattan or 3.8, 3.9, approximately that value. So magnetic moment will be 3.83 Bohr Manhattan. Number of unpaired electrons will be 3. Inner orbital complex, spin not defined. Hybridization is G2sp3. Right? So can you try to find out, is this clear, students? Is the example clear or not? Yes, I will say G2sp3, very good. Very simple case. Right, all the points, whatever we have discussed, the same points. In case of D3, don't see ligand according to CFT, T2G3 Eg0. Now we should comment more according to CFT. You should not say like ammonia is a strong field ligand, so pairing of electrons occurs. No, not like that. So based on the CFT only, you have to argue. Try to comment on this. CrNH3 taken 6 2 plus, right? So here chromium is in +2 state. Chromium electronic configuration. Argon 4s1 3d5. Chromium in the +2 state. Argon 4s0 3d4. D4 system, ammonia is strong field ligand. D4 strong field ligand. What will happen? Your Eg level, your T2G level. So first, second, third, fourth electron will pair up. So you have electronic configuration of T2G4 EG0. So what type of hybridization? D2sp3 because because inner orbitals are available. What is the geometry? Octahedral. Low spin or high spin complex. Now we can define because of strong field ligand only the pairing of electron happened. No, so that is why it should be a low spin complex. Number of very good. Low spin complex. Number of unpaired electrons is two unpaired electrons. So magnetic moment will be spin only magnetic moment, not the total magnetic moment. Spin only magnetic moment will be under root of n into n plus 2 Bohr magneton. So 2 unpaired electrons means 2.83 Bohr magneton. Very simple. Can I proceed further, students? All of you should respond.
Yes, sir.
Yes.
Yes, sir.
Yes, very good. Try to answer this. Which of the following is an inner orbital complex? Within 10 seconds, you have to answer this.
Third option.
So Aditi answered within a second only. Very good. So how we can answer this? How, Aditi? Sahil also says third option.
Sir, D5.
Yeah, manganese is in +3 state. So +3 D5 or D4?
Sir, D4.
Yeah, D4. Then?
Sir, then it is low spin complex.
Yeah. So only point is inner orbital complex means EG should be empty. When is EG empty? When electrons don't go to EG. When the electrons won't go to EG? When we have a strong field ligand. Look at the ligands. Fluorine, H2O, cyanide, which is a strong field ligand. Yes or no? Cyanide is a strong field ligand. Fluorine, H2O, all those are weak field ligands. So inner orbital complex means EG level should be vacant. EG level should be vacant means electrons are not going into EG. Electrons not going into EG means what? They are simply pairing up in the T2G. So write down the electronic configurations where the electron is pairing up in the presence of strong field ligand only. Only one strong field ligand is given. So that will be your MnCN taken 6 3 minus. You should not directly conclude like that. With that ideology, you have to proceed. Write the electronic configuration and do that. First, my first pick is option 3. So now I will be writing the electronic configuration of manganese +3. So D4 I will get, and then if I do it, I will be getting inner orbital complex. So that is my right option. Like that, I will proceed. Yeah. Then calculate CFSE for octahedral complex. Coordination number 6. This is the formula I have told you. What was the formula? If you remember, CFSE is equals to minus 0.4 delta naught into number of electrons in T2G plus 0.6 into delta naught plus number of electrons in EG plus NP. The same formula we have written, students, but with respect to X and Y. So minus 0.4x plus 0.6y into delta naught plus NP you write down. This is easy to remember. X stands for, or if you want to remove X and Y, you can place number of electrons in T2G, number of electrons in EG. CFSE is equals to minus 0.4 into number of electrons in T2G plus 0.6 into number of electrons in EG whole delta naught plus NP. So this is nothing but your crystal field stabilization energy. So this NP refers to the N stands for the number of electron pairs, total number of electron pairs. P stands for pairing energy. Delta naught crystal field splitting energy in the case of octahedral complex. NT2G number of electrons in T2G, NEG number of electrons in EG. Is that clear, students?
Yes, sir.
Yes, try to solve this question then. Calculate CFSE for D6 octahedral low spin. D6 they have said octahedral complex, low spin complex. Calculate CFSE. D6 octahedral means what I can do? I can just split down the 5 d orbitals into two levels. One is Eg, other is T2g. I have to fill 6 electrons. First electron, second electron, third electron I have filled. No issues. But fourth, fifth, sixth filling, how to do it? So for that they have given some information. Low spin. Low spin means what? Low spin means pairing up. Yes, very good. So D6 will be having now electronic configuration of T2g6, Eg0 in the case of strong field ligand or low spin complex. So what is your CFSE now? CFSE is equals to minus 0.4 into number of electrons in the T2g. How many electrons in the T2g? 6 plus 0.6 into number of electrons in the Eg. How many electrons in the Eg? 0. Whole multiplied by delta naught plus NP. What is N? Number of electron pairs. How many electron pairs are there? 3p. Yes or no? So minus 2.4 delta naught plus 3p. This is your CFSE. Got it, Ayushi?
Yes, sir.
Yes. So low spin means pairing occurred. So if you take the reverse, like if you fill the electrons in the Eg, you will be getting the different value for delta naught, which is obviously wrong. So here you consider 3p. Try to solve this. What is the CFSE of FeCN6 3 minus? Try to solve this. What is the CFSE of FeCN6 3 minus? What is the CFSE of FeCN6 3 minus? You have to say your answer.
Minus 2 delta naught plus 2p.
So one answer I got, minus 2 delta naught plus 2p. Let us try to figure out that. So FeCN6 3 minus 1 iron is there, 1 into x plus 3 6 cyanides, 6 into minus 1, that is equals to minus 3. So x should be is equal to plus 6 minus 3, that would be plus 3. So iron is in plus 3 state, Fe is in plus 3 state. What is the electronic configuration of Fe? Argon 4s2 3d6 plus 3 state means argon 4s0 3d5. So d5 system, d5. And cyanide is a strong field ligand or weak field ligand?
Strong field.
Strong field ligand. Very good. D5, 1, 2, 3, 4th and 5th they are going to be paired up. 4th and 5th they are going to be paired up. So CFSE minus 0.4 into number of electrons in T2g is how many? 5, because the electronic configuration is T2g 5, Eg 0, plus 0.6 into number of electrons in the Eg. How many? No electrons, 0. Whole multiplied by delta naught plus number of electron pairs 2, so 2p. So minus 2 delta naught plus 2p. So this is your right answer. Okay. Very good. The CFSE of FeCN6 whole 3 minus would be minus 2 delta naught plus 2p. That is your right answer. And next to come, students, factors affecting the splitting energy So we have discussed octahedral complexes, tetrahedral complexes, and square planar complexes, where the splitting is greatest. If you try to compare, the splitting is greatest in square planar or octahedral or tetrahedral.
Octahedral.
Write down this. Splitting energy is directly proportional to charge of central metal ion. Splitting energy directly proportional to ligand strength. Splitting energy directly proportional to effective nuclear charge of central metal ion. Because if the charge on the central metal ion is greater, the ligands are coming greatly, so they repel the inner d electrons greatly, so splitting will be high. If the ligand is a strong field ligand, again it repels greatly, so repulsion would be high. Effective nuclear charge great for the central metal means ligands attracted greatly, so again repulsions are high, so d orbital split greatly. So last class itself we have seen, so among octahedral and tetrahedral, octahedral will be having greater splitting. Among square planar and octahedral, square planar will be having greater splitting, because last class itself I have told you, like the EG and T2G, they will further split. Yes or no? So this is your dx square minus y square. This is your dxy. This is your dz square. This is your dyz, dzx. So this is nothing but your square planar splitting, delta sp. This is your octahedral, delta O. So delta square planar splitting will be greater when compared to delta O, and experimentally this value is found to be delta square planar is 1.3 times that of delta naught. Tetrahedral splitting, delta T is equal to 4/9 times that of delta naught. Tetrahedral splitting will be 4/9 times that of delta naught. Order of splitting depends upon geometry. Write down these points. Order of splitting depends upon geometry. Square planar splitting will be highest, then octahedral splitting, then tetrahedral splitting. Tetrahedral would be, the splitting in tetrahedral would be 4/9 times that of the splitting in the octahedral. Splitting in square planar is 1.3 times that of splitting in octahedral. And splitting energy is directly proportional to charge of central metal ion. Splitting energy directly proportional to ligand strength. Splitting energy directly proportional to effective nuclear charge of central metal ion. All of you note down these points. With these points only we are going to comment upon stability of complexes. Stability of complex, again same things. Charge of central metal ion directly proportional to stability of complex. Ligand strength directly proportional to stability of complex. Z effective of central metal ion directly proportional to stability of complex. Similarly, number of chelation rings directly proportional to stability of complex. Like that, we'll be having some 4 to 5 points which can explain the stability of complexes formed. It is not just like complex formed, hybridization given, inner orbital, outer orbital, but you should also explain why the complex is stable. And there are few reasons why it is stable. Is that noted? Can I proceed further?
Yes, sir. Yes, sir.
Yes. Yeah, this is what I'm talking about. Factors affecting stability. Write down these 5 factors. The 3 factors are already same. And the 2 more points are synergic bonding and number of chelate rings. The whatever the complex you are talking about, that complex is more stable if it has synergic bonding, like back bonding. The pi bonding also available means stability gain. Stability of complex is directly proportional to number of chelation rings or number of chelate rings. More the number of rings, more the stability. Stability of complex is directly proportional to charge of metal ion. Like if we have metal ion Mn plus, if the charge on the metal ion is great, obviously it will attract the ligand greatly. Yes or no? So if the metal ion has more charge, it will attract the ligand greatly. So obviously the ligand metal bond is formed easily. So stability of the complex is great. Ligand strength, now same metal ion, but ligand is a strong field ligand. So that means earlier we have the metal ion which is attracting the ligand greatly. Now the metal ion, now the ligand itself is going to be the metal ion because it's a strong field ligand. So ligand strength, the charge of metal ion, effective nuclear charge of central metal ion, all these things They are also directly proportional to stability of complexes as well as splitting. And two more points which you have added extra is synergic bonding. Synergic bonding means we all know pi donation, pi back donation. So pi character leading to the more bond strength. Obviously, greater is the stability. Chelaten rings. So number of rings formed greater means obviously greater is the stability. Listed down all these 5 points. Based on these 5 points, you can explain the stability of the complex. Done, Vaidehi?
Yes, sir.
Yes. Yes, Prachi, ligand strength means strong field ligand is going to form a bond easily. So strength of the ligand greater means the stability of the complex is high. Understood? Ligand strength means strong field ligand is a stronger ligand which has more field. So obviously it has more tendency to form a bond with the metal. So there the whatever the complex is formed, that is going to be stable. Okay. Determine the correct order of stability among this first question you try to solve. FeCN6 3 minus, FeC2O4 taken 3 minus, which is more stable? FeCN6 3 minus, FeC2O4 taken 3 minus. Which is more stable? Aishi says 1. Prachi says 1. Faizan says 2. Only 2 are there, no? 2 complexes. Reasons you have to give. Nandana says 2. So reason is simple. What was the reason you can give? Yeah, because of the formation of chelate ring, FeC2O4 taken thrice. C2O4 is a what type of ligand? Oxalate, right? C double bond O minus, C double bond O minus. So that is going to be forming a ring. A 5-membered ring is going to be formed when you have one bidentate oxalate ion. So this bidentate ion will be forming one ring with the metal. So FeC2O4 taken thrice will be somewhat like this. Yes or no? This is nothing but your ligand. So yeah, Aishi, whenever you have chelation and ligand strength, chelation is prioritized. Yes or no? C2O4 2 minus is forming rings. Because of ring formation, stability is gained. Okay. Try to comment on the second option. This is the structure of your chelation complex FeC2O4 taken thrice 3 minus. FeH2O taken 6 3 plus, FeN taken 3 plus, Fe-diene taken 2 3 plus. Again, they are taking H2 as one ligand, monodentate ligand. En, ethylene diamine as one ligand, bidentate ligand. Diene, diethylene triamine, that is a tridentate ligand. Again, there is a something they are talking about the rings. So greater the number of rings, greater will be the stability. How many rings here? H2O. H2O means how many rings, students? 0 rings because no chelation. Ethylene diamine, what is the number of chelate rings? Fe, E and taken the 3 plus. How many rings are formed in this complex? Fe, E and taken 3 plus. Chelation rings is equals to denticity minus 1. What is the denticity of ethylene diamine? 2 minus 1, that is equals to 1. So one ring is going to be formed for one ethylene diamine. Therefore, for 3 ENs, how many rings are formed? 3 rings are formed. Understood now? So number of rings formed is not with respect to only one ligand, no. So we have how many ethylene diamonds? 3 ethylene diamonds are there. Every ethylene diamond is forming one ring. So we have 3 ethylene diamonds. So they will form 3 rings. Diethylene triamide. So what is a chelation?
3 minus 1.
Chelation is,
Minus 1.
yeah, 3 minus 1, that is equals to 2. So 2 rings are going to be formed from each diethylene triamine. How many such diethylene diamonds are there?
4 rings.
4
Yeah,
rings.
for 2 dienes, you will be getting 2 into 2, that will be 4 rings. So greater the number of rings, greater the stability. So Fe diene taken twice 3 plus is more stable. Then FeEn taken thrice 3 plus is stable. Then FeH2O taken 6 3 plus is stable. So this is the order of stability. Got it? Got it, students? Can I proceed further?
Yes.
Yes, sir.
Yes.
Yes, sir.
So whenever they are giving two complexes where one of the complex is having a bidentate ligand or tridentate ligand which has a capacity to form rings, immediately you should think of chelation. Determine the correct order of stability. Try to figure it out now. Determine the correct order of stability. Determine the correct order of stability. In that you have seen COH2 taken 6 2 plus, COH2 taken 6 3 plus. So based on which point you can say COH2 taken 6 3 plus is more?
Charge on central metal ion.
Yeah, charge on the central metal ion. Next, NaH2 taken 6 2 plus, NaNH3 taken 6 2 plus, NaH2 taken 6 4 minus. Here what is the oxygen state of nickel? Plus 2. Here also plus 2. Here also plus 2. Everywhere you have nickel in the plus 2 state. So charge is same and same nickel. So effective nuclear charge, that is also same, because in case if you have nickel, palladium, platinum, then the effective nuclear charge might change. Charge is same, effective nuclear charge same. H2O, NH3, NO2 all are monodentate ligands. So no chelation, no back donation, no spectrochemical, no synergic bonding also. So only thing which is differing is ligand strength. So which is a strong field ligand? H2O, NH3, NO2, which has the highest strength? NO2 minus, then NH3, then H2O. So based on ligand strength, we can compare which complex is more stable and why it is so. Got it now, students? How to compare the spectrochemical series orders with respect to stabilities, or chelation rings with respect to stabilities, charge on central metal ions. So let us proceed then. So the next point is crystal field splitting in tetrahedral complex. This is simple, as I have told you already. Now we are going to look at the animation. In the tetrahedral complex, the ligands are not approaching along the axis, they are approaching in between the axis. So we take a cube now. Ligands are approaching from these positions, whereas central metal ion is at the origin. Ligands are approaching from all these positions. So it can be shown that in tetrahedral structure, none of the d orbitals points exactly towards the ligands. None of the d orbitals points exactly towards the ligands. When ligands approaches, they are more close to dxy, dyz, dzx in comparison to dx square minus y square and dz square. Because the dxy, dyz, dzx are in between the axis and dz square and dx square minus y square are along the axis. That is why the T2G sets here in the tetrahedral we call T2 set, EG as E set. So the T2 set will have more energy when compared to E set. So thus the d orbitals are also split into two groups, but in the reverse order of that octahedral complex. The three orbitals dxy, dyz, dzx designated are now has higher energy than those that of two orbitals. Simple point what they are trying to say is, here now you will have dxy, dyz, dzx higher, dx square minus y square, dz square lower. This is T2 set, this is E set. Got this point or not? See, ligands are not approaching along the axis. That is the point. So since ligands are not approaching along the axis, you will be having those d orbitals with increase in energy which have their lobes in between the axis, not along the axis. Look at the animation. So it resembles with your similar to your solid state, yes or no? So whenever you try to connect all this, what you are going to generate? Like these are alternating corners, right? Try to connect all these alternating corners. What type of figure you will generate? A tetrahedral complex, right? A tetrahedron is going to be generated. In the same way, if you remember, in the solid state, we have figured out tetrahedral voids, octahedral voids. Can I ask you a question regarding solid states, like where the tetrahedral voids are present?
Along the diagonal.
On the diagonals of what?
Of the lattice.
Very good. How many are there in total?
2 on each.
So you'll be having 8 tetrahedral voids in total. 4, like a 2. There are 4 body diagonals, right? On every body diagonal, you are going to have 2 tetrahedral voids. And how do you know that the tetrahedral voids are on the diagonals? So to figure out the position of tetrahedral voids, what we have done is, we have figured out where the tetrahedrons are. We have divided the total cube into 8 small cubes. In every small cube, you are generating a tetrahedron if you try to connect the alternating corners. So because there is a tetrahedron, there should be some empty space with that tetrahedron. So that should be a tetrahedral void. Like that, the derivation has been done in solid state. Same here, similar to that. So we have a tetrahedron now. And if you look at the approach is not along the axis. So those d orbitals whose lobes are not along the axis, they will experience more repulsion. Right, students? So this is your, in the absence of ligand field, d orbitals of metal, what are they going to have? They are going to have, all of them will be having increased energy. So what is this? In the presence of ligand field, energy of d orbitals is increased. What type of field is this?
Spherical field.
Spherical field, because you are applying field from all the directions. Next, you have seen the splitting. dxy, dyz, dzx, they will be high. Dx square minus y square, dz square, that will be low. In the animation, they have given this is high, or these two are having same energy. But in reality, the E set, that will be high in energy when compared to no field. When compared to no field. So this is your barycenter, like where the energy of your 5 d orbitals are present. Delta T, that is nothing but your crystal field splitting energy of tetrahedral complexes. This is T2 instead of T2G. This is E instead of Eg. Differentiation is there when compared to your octahedral and tetrahedral. Now, can you calculate what is CFSE? Everything is same, right? Everything is same, just the difference or opposite to that of your octahedral. CFSE, how we can calculate? Let us say there are some Ne electrons in the E and Nt electrons in the T2. So first let us say Ne in the Ne electrons in the Eg set or E set, similar to Eg set. And what is the decrease in energy of this particular E set? Energy is decreased, so that is why I write minus symbol. How much is decreased? I don't know. What I know, whatever the energy decreased, that has to be compensated by the 3d orbitals. So 2d orbitals are lowered in energy. How much the energy is lowered, we don't know. But what we can say, the energy lowered for these 2d orbitals, that should be compensating with the increase in energy for the 3d orbitals. So 3 by 5 delta T plus delta T, why? Because it is tetrahedral splitting, plus number of electrons in T2. Energy is increased for T2, so plus sign. How much is increased, I don't know. But how much is increased, that will be obviously compensated by the decrease in energy by the Eg or E. So plus how many in the Eg? 2 by 5 delta T. And obviously Np stands for number of electron pairs. Try to solve this, you will be getting minus 0.6 Ne plus 0.4 Nt and T2. T2 stands for number of electrons in the T2 whole delta T plus Np. This is nothing but your CFSE, crystal field splitting energy. Minus 0.6 Ne plus 0.4 Nt2 whole delta T, not delta naught. Delta naught means octahedral splitting, delta T means tetrahedral splitting plus Np. This is your crystal field stabilization energy or splitting energy in the case of your tetrahedral complexes. If you look at octahedral, what is happening in octahedral, students? In octahedral, minus 0.4 Nt2G plus 0.6 Neg whole delta naught plus Np. Only difference is here you have the minus symbol or not. So you can multiply this with throughout with minus. So octahedral, if you multiply with minus for this, it becomes plus 0.4 Nt2. So that's what we have in tetrahedral. Minus 0.6 Ne. That's what we have in tetrahedral. Delta naught is replaced by delta T plus Np. Because octahedral and tetrahedral splitting are reverse, no. That's why we are having just an opposite things. Is that clear? All of you note it down and let me know. Then next thing is color property, which was one of the drawback of valence bond theory. Yes or no? The color property is a drawback of valence bond theory. Complex compounds are mainly colored due to DD transitions. So up to now we have seen that the d orbitals are not degenerate. They are going to be splitting into two levels in the octahedral and tetrahedral. So from the lower energy d orbital set to the higher energy d orbital set, the electron can go whenever it absorbs energy from the outsource, like from the light energy or thermal energy. So complex compounds are colored due to DD transitions. Very, very interesting. So ligand is actually giving the electrons to the metal ion. So the dx square minus y square, dz square, they are in the EG set. dxy, dyz, dzx, they are in the T2G set, as far as you consider the octahedral complex. So let us say there is an electron. There's an electron in the T2G, like D1 configuration you consider first. And now this electron in the T2G, it got energy from some outsource like sunlight. It went to the EG. Yes or no? In D0 and D10 electronic configuration, DD transition is not possible, because D0 means there is no D electron. If there is no D electron, how the excitation is possible? That is not happening. D10, every electron in T2G and every electron in EG are paired up. There is no unpaired electron, and there is no vacant orbital, or there is no pairing possibility also. So D0 and D10 electronic configuration, DD transition is not possible. As I have told you in the D block elements also, if you remember, what I have told you in the D block when I am explaining color, whatever the color you are seeing, that is not the color absorbed by the electron. That is not the color or wavelength absorbed by the electron to go into the high range level. What is the color you are seeing? The color you are seeing is the wavelength left out by the electron. Are you understanding this property or not? If I have an electron, yeah, if I have an electron, this is your T2G, or this is your T2G, this is your EG. From here I am giving some 100 units of energy. Assume 100 units of energy will correspond to particular lambda, because E is equal to h mu. That is equal to hc by lambda. Whatever the energy we are saying, that will be corresponding to specific lambda. Specific lambda corresponds to specific color. So we have an electron in the T2G. I am giving 100 units of energy. With this 100 units, let us say 20 units electron required to go to the EG level. So from this 100 units, electron taken 20 units, and it went to the high range level. It is not stable in the high range level. It will come back to the low range level. That is a different scenario that will happen later. But out of this 100 units, if 20 units were taken by the electron, what happened to the remaining 80 units? That will be lost, right? That will be simply passing through the complex. I am standing somewhere here. Yes or no? I am standing, observer is standing somewhere here. Source is somewhere here. From the source, we are giving 100 units. Out of 100 units, 20 units taken by electron, 80 units left out. So observer sees what? 80 units of energy. So observer sees the color corresponding to 80 units of energy. So observer sees the color corresponding to the left out radiation, not the radiation absorbed by the electron. Understood this point or not?
Yes, sir. Yes, sir.
Yes, Vaidehi, very good. What about others? All of you respond. Only then the class would be effective. You will gain more knowledge. Okay.
Yes, sir.
So color of complex compounds depends on absorbed energy and absorbed wavelength. So you, sir, just now you said it is not depending upon absorbed energy. Now again you are saying it depends upon absorbed energy. What do you want to say? You may ask a question like this. I'm not saying it is not depending upon absorbed energy. What I mean to say is, whatever the color you are seeing, that is the color of left out radiation. What do you mean by left out radiation? That means radiation not absorbed by the electron. In case if you have a strong field ligand, the splitting is very, very high. Electron is somewhere here. Out of 100 units, earlier let us say it is absorbing 20 units. It goes to the high range level. Now if I take a different complex, it will absorb some 40 units. It will go to the high range level. So here, what is the left out radiation in the first scenario? 100 units is given, 20 absorbed. How much is left out? 80 left out. 100 units is given, 40 absorbed. How much is left out? 60 left out. So based on the absorption, the amount of energy left out, that is also changing. So indirectly, although you see the color corresponding to 60 units of energy, but indirectly the absorbed energy, that also determines the color. Okay. So color of complex compound depends on absorbed energy also and absorbed wavelength. Energy absorbed E is equal to Hc by lambda. So energy absorbed should be inversely proportional to lambda absorbed. In the case of strong field ligand, absorbed energy highest means absorbed wavelength lowest. Obviously, this is true. In the case of strong field ligand means difference in the T2G and EG levels is highest. This is T2G, let us say, this is EG, let us say. So strong field ligand, T2G and EG difference is highest. So electron has to gain more energy. So more energy means energy absorption should be high. If the energy absorption is high, what happens to lambda? Lambda should be weak. Weak field ligand means less energy difference. Less energy difference means energy absorbed is less. So lambda should be high. Lambda should be high. So example, out of these two complexes, which complex will absorb more lambda? Try to answer this. Okay. NiH2O taken 6, NiH3, NH3 taken 6 2 plus, NiNO2 taken 6 4 minus. Among these three complexes, or arrange these three complexes in the increasing order of their wavelengths absorbed. If lambda 1, I can say lambda 1 is the wavelength absorbed by this complex, lambda 2 is the wavelength absorbed by this complex, lambda 3 is the wavelength absorbed by this complex. Arrange lambda 1, lambda 2, lambda 3 in the increasing order.
That's 3
Which
to
is a-
1. 3 to 1.
Which is the strongest ligand?
NO2.
NO2 minus is a strongest ligand. So obviously energy should be highest. So its lambda should be lowest. So lambda 3 weakest. Then lambda 2, then lambda 1. So this is the correct order. Got it? Strength of ligand increases, so energy increases, so lambda decreases. So lambda 3 is least, then lambda 2, then lambda 1, or you can say lambda 1 is highest, then lambda 2, then lambda 3. Energy means energy absorbed means based on the ligand strength you can compare. Nandana got it or not? 1, 2, 3, lambda 1, lambda 2, lambda 3. Among these three, lambda 1 is highest, then lambda 2, then lambda 3. I said increasing order. So lambda 3, lambda 2, lambda 1.
Yes, sir.
Yes.
Yes, sir. Yes, sir.
Yes, very good. Yeah, for example, complementary color of green is purple. Let us look at now the same thing which I am going to say. I am giving VIBGYOR of radiation, all the colors, white light I am passing. That is actually passed through some complex which was in a test tube. In this complex absorbing some green portion. Yes or no? So green portion of that particular VIBGYOR has been absorbed by this particular complex. But the complex look what type of color? It looks violet in color. Look carefully. Yes or no? It is purple in color, right? Purple in color. Look carefully. The same thing what I am saying. If green portion of the VIBGYOR has been absorbed, you are not having the complex as green in color. You are having the complex as purple in color. Yes or no? Because you are not seeing the color absorbed. You are seeing the color of the left out radiation. You are not seeing the color corresponding to absorbed radiation. You are seeing the color corresponding to left out radiation. But the color, what you are saying, that will be depending upon absorbed energy. Why? Because if absorbed radiation changes, the emitted radiation obviously changes. So that's what they have been explained with a beautiful animation. So you have VIBGYOR of radiation. Now the green portion has been absorbed by the complex, and the complex is showing the purple color. So green and purple, they are complementary colors. Write down this circle. These are no complementary colors. If the complex absorbs violet, it should be yellowish green. If it is indigo, it should be yellow. Blue, orange. Red, bluish green. Okay. Purple, green. So these are all your complementary colors. These are all your complementary colors. Is that clear, students? Note it down. Try to answer this. Correct increasing order of wavelengths of absorption in the visible region of complexes of CO3 plus. Yeah, Keshav has a question. Sir, if green color is absorbed, what about other color? That is left out. Yes or no? Green color absorbed. Why only green color absorbed? You can question yourself. Because in this complex, you have some d orbitals which are splitted. Let us say this is an octahedral complex. They have just given MLX whole plus n. Let us say this is an octahedral complex. So splitting happened into T2G and EG. So there is some energy difference between T2G and EG. So this energy difference, let us say, corresponding to green color. So green color has been absorbed. So whatever the left out radiation, that is what are the remaining radiation that is left out. But what you will show, you will not show all the colors with green. At the green, you will not have dark band. It is not like spectroscopy. You will be showing the complementary color of green, which is going to be a purple. Got it?
Yes, sir. Yes, sir.
Yes. Why only green color? Why? Because the energy difference between T2G and EG is such that. Try to answer this. Correct increasing order for the wavelengths of absorption in the visible region. Same thing, wavelengths they are saying. Increasing order of wavelengths. Increasing order of wavelengths means decreasing order of energy. We have to arrange them in the decreasing order of energy. How we can arrange?
The fourth
Yes.
option.
Fourth option. So which is the strongest ligand? Ethylene diamine, ammonia. Among ethylene diamine and ammonia, which is strongest ligand?
Ethylene diamine.
Ethylene diamine. Yes or no? Ethylene diamine is strongest ligand. So strongest ligand means obviously weakest or lowest wavelength. So option 4 will be right option. So increasing order of wavelength means decreasing order of energy, which means decreasing order of ligand strength. Very simple, right? And this is also important. The presence of a ligand is required for a DD transition. What happened if we do not have a ligand? If we do not have a ligand, there is no DD splitting at all. There is no splitting in the d orbitals. If there is no splitting in the d orbitals, where comes the DD transition? That is not possible, right? So presence of ligand is required. So titanium trichloride, that is colorless. Whenever you add water, you will form TiH2O taken 6Cl3. Here also titanium is in +3 state. Here also titanium is in +3 state. Titanium is the +3 state. What is the electronic configuration? D1 or D2 or D3?
D1.
D1. So we have a D electron. So DD transition is possible. But DD transition is possible only in the complexes. TiCl3 is colorless because it is not a complex. TiCl3.6H2O, again if you heat it, again you form titanium trichloride, which is again colorless. So presence of ligand is required for DD transitions. In the presence of ligands only, you will have complexes. Whenever you have complexes, then only d orbital split. CuSO4 is colorless but hydrated. Whenever you add copper sulfate to water, you will be getting CuSO4.5H2O, which is light blue in color. You have taken the advantage of light blue color of CuSO4 in your salt analysis experiments as well. Again, if you heat it, you again get copper sulfate, which is again colorless in nature. So presence of ligand, that is required for your DD transition. Fine, students. This is about your color property, and we do have some complexes which are not colored, which should not be colored according to DT transitions, but are colored based on your charge transfer phenomena, which we have discussed, like K2Cr2O7, KMnO4. We will discuss that complexes and then proceed with your optical activity, like isomerism part, optical isomerism, geometrical isomerism, and structural isomerism also. Fine, thank you all. We'll discuss in the next class.
Thank you,
Thanks.
sir.
Thank you, sir.
Thank you, sir.
Keshav, not only water, it can be any ligand. Okay.
Okay, sir.
Okay. Point is, splitting of d orbital should happen. If splitting occurs, then only DD transitions are going to happen. If not, no DD transition.
Okay, sir. Thank you.
Okay, fine. Thank you.